Hello, I'm Reese Wilson, and I'm doing my Intro to Materials final project on magnetism at various temperatures. I'm going to give a brief refresher on how magnets work. Magnets contain two poles called the north and south poles that exert force on objects with other magnetic properties. So with that being said, opposite poles will attract. So the north pole will be attracted to the south pole while the same sides will repel. So therefore, a north pole and a north pole of a magnet will not stick to each other or attract. Or same goes for south pole and south pole. On to my experiment. So in today's experiment, I'm going to test the strength of neodymium magnets at various temperatures to see if temperature plays a role within magnetism. I'm going to do this by heating and cooling the neodymium magnet bars at various temperatures, such as in my fridge, freezer, in a pot of boiling water, and then one at just regular room temperature. And then I'm going to place them on an apparatus of an instrument that measures length, which is actually my bump board, and I'm going to sit that next to a compass. The plan is to analyze the trends that are found in the experiment and provide reasoning for why the trends exist. Experiment I chose to use a compass because I felt it would be easiest to show when the magnetic field was present within the experiment because of the needle inside of the compass that contains a magnet on both ends. So whenever it moves, whichever direction it goes, it shows which way the magnetic field is acting on the needle. Below show the conditions in which the neodymium magnet bar was placed into. So I put the neodymium magnet bars into a plastic bag and then placed them inside the fridge, which was 38 degrees Fahrenheit, and then one in the freezer, which was -2 degrees Fahrenheit. Okay, this is showing my experiment. So there's the compass. You want to make sure that the needle is directly lined up with the 0 at north, and we're going to start with the freezer temperature magnet. So you want to slide it down the measuring stick until you see the compass needle move. So I see it move there, and the distance is kind of blurry, you can't see it, but it was 26 centimeters for the -2 degrees Fahrenheit. And now we're doing the fridge temperature, which was 38 degrees Fahrenheit. And repeating the same thing. Watch the needle until the needle moves towards the magnet. And the measurement for the 38 degrees Fahrenheit was 23 centimeters. And I moved the compass there to make sure that it was zeroed out from the last one. And now we're doing this with room temperature, 75 degrees Fahrenheit. 72 degrees Fahrenheit, sorry. And the distance for that one was 21 centimeters. So another step I added into this experiment was I placed a pan of boiling water with the stove temperature on high and placed the magnet in the boiling water for approximately 30 seconds. For some reason it's not shown in the video, but after I took the magnet out of the boiling water, I put a thermometer to it and it showed a temperature of 157 degrees Fahrenheit. And here I'm having to use the tongs, obviously, so it doesn't burn me. But if you look closely, you can see that when the compass needle moves, it actually repels away from the magnet. That's because I have the north pole facing the compass, and the distance that read there was 19 centimeters. Here are the results from the 4 different trials. As you can see, as the temperature began to increase, the distance would have to be closer to the compass for the magnetic field to appear within the experiment. A picture of the graph of the results. I feel this is a better way to show that as the temperature increased, the distance from the compass, the magnet's distance from the compass, sorry, would have to be closer for the magnetic field. I feel like it's just an easier way to show it. Moving on to the reasoning behind the trend shown in the experiments, which was, as the temperature begins to increase, the magnetic strength will decrease. This is because when you heat a magnet, it creates a thermal energy that causes the atoms inside of a magnet to begin to vibrate. This disrupts the magnetic dipoles. The temperature at which the material loses its magnetic property is called a Curie point. This happens because the magnetic dipoles become so disrupted they are not able to return to their original state. The Curie point of a neodymium magnet bar is around 320 degrees. I was not able to reach this during the experiment as I only had access to my household supplies. And here are the sources that I used for this experiment.